pure water, and you pour out half of it, is it still pure? And the answer is, yeah, it's still pure. So it didn't change the concentration. It's still 100% water. So it doesn't adding more water or removing water doesn't change its activity. Its activity would be based on how concentrated it is. The more concentrated, the more active something's going to be. At all. No. No, but you need to have it present, though. So if there's no calcium carbonate, you're not going to get any reaction. But having more or less, it doesn't make it more. It's going to take more energy to convert it into calcium oxide and CO2. That particular reaction there, the calcium carbonate goes to calcium oxide plus CO2, is ranked as one of the, I think the top 10 reactions in history. That reaction, well, at least for technology, that reaction led to concrete development. Concrete was a major step forward in structure, structural strength versus wood. So that's an important reaction. So the test had a lot of based on that particular reaction. This is one of the ones that have been studied a lot because that was developed by the Romans. Okay, other questions? Okay, well, if other questions come up, let me know. Well, we're going to take a look at our titration data today and analyze that. But also, I was thinking we'll have a preparatory quiz for tomorrow's test. So we'll have a quiz, let's say at the end. It'll be open book, open notes, and you can also collaborate with other people if you wish, for this particular quiz. It's something that should be able to do. We'll do it later. We're going to the computer lab today, but before we go there, I want to talk about what we're doing. We do a pH titration curve. We're going to plot the pH versus milliliters of sodium hydroxide solution here. And we're going to have data, or raw data like this. So the first thing we need to do is we need to draw a line through our data. And the default for Excel is it draws straight lines between segments. And so it's not going to look very smooth because we'll get a straight line here and then there's another straight line. But instead of doing straight lines, what we're going to do is we're just going to do a smooth curve. This is not a mathematical fit. This is just trying to smooth out the data here. It's still going to pass through all the data points. So we have different ways of fitting curves. One way is we can define some curve and then via some mathematical equation, then just try to fit it via the mathematical equation. That's one way. Another way is this. This way is not fitting it to any mathematical equation. In fact, to define the pH curve with a mathematical equation, we have to divide it into the regions. So this is why I divided it into, at least for a monoprotic acid, into the separate regions where we had the chapter 16 acid solution, and then we had the buffer region. The buffer region is after the initial reaction. We're left with a buffer mixture, and then the base solution, and then the excess strong base solution. And so we would define this with 1, 2, 3, 4 different mathematical equations to fit this entire curve. And so we could do that, but we're not going to do that. We're just going to do the smooth fit function. And so when you add a line, we'll do a smooth fit rather than trying to fit it to mathematical. Now when you use Excel to try to fit it to a mathematical function, you might be familiar with the trend line function. Have you guys used the trend line function in Excel? Yeah. So normally we try to fit it to, let's say, a linear trend line. You know, if we fit this to a linear trend line, it would not look very good. It would just be a straight line that goes like this, something like this. But we could go to higher order polynomials. The highest order polynomial we could do in trend line is, I think, 6th order. But even if you try to fit this with the 6th order, it's not going to look very good. You could try to fit it with a 6th order polynomial and see if it fits, but it's not going to fit. It's going to be off. We also use the trend line and R squared. Are you guys familiar with R squared, the correlation? Yeah? R squared, if you have an R squared of 1, it's a perfect fit. Yeah. And so normally in science we look for multiple nines, like 0.999, you know, 3 nines or something, at least 1 9. If you start getting to 0.8, it's not very good, the correlation. And so what we're going to do is the smooth fit. We're not going to fit it to a trend line, although you could try to fit it to a trend line and see if it fits. You know, if it does fit the mathematical function, that is, we get a decent trend line with a decent R squared value, R squared, you know, being close to 1 in the high 9s, 99%, I mean. But then we could define this curve mathematically, and if we can define the curve mathematically, then we don't have to analyze it graphically. We can analyze it mathematically. That is, if we generate an equation like this, and then we want to find how many milliliters, we'll just plug it into the equations. If we want to find the pH, we plug it into an equation. If we want to find out where this point of inflection is here, you know, this point is very important. We call this the equivalence point. Now the equivalence point here may or may not correspond to a data point. So let's say this equivalence point here is bordered by these 2 data points here. So we have a data point here and a data point here, but we don't have a data point here, right in the center. We don't choose the data point, we choose the point on the line. So this is why we need a mathematical function, so we can determine where this is, you know, in terms of milliliters and pH here. Since the data does not correspond, the data just jump past it. And so most often you aren't going to have a data point right at the equivalence point. And if you do have a data point right at the equivalence point, that's coincidental. You know, it's just by chance that had happened, but it's very unlikely to happen. And so what we're going to do is we're going to analyze this graphically. You know, since we're doing the smooth fit, and we aren't analyzing it mathematically, what we're going to have to do is a graphical analysis. And a graphical analysis is, once the smooth fit is drawn there, we're going to eyeball the inflection point. The inflection point is where, take a look at what happens to the slope of this. The slope of this steepens, and it gets steeper and steeper, and then when you hit the inflection point here, it's going to be the steepest, and then it's going to gradually go down. So the slope of this gradually goes down and then flattens out completely out here. And so you're looking at this point where it transitions from increasing slope to a decreasing slope right here. And so what you're going to do is you're going to eyeball this point, and then you're going to draw a line. We could draw lines in Excel here, like this. And then what we're going to do is we're going to make grid lines. You know, in Excel you can set the grid lines here on the chart. And so we're going to have enough grid lines that we can determine the volume here precisely. And so, and then you could change the spacing on the grid lines. What we want to know is we want to know how many milliliters this is to 2 decimal places. So we need to make sure that, you know, the last digit here, according to the rules of sig figs, is what? What do we call the last digit according to the rules of sig figs?
Is it like uncertain?
Yeah, it's called the uncertain digit. Good. It's the uncertain digit. And uncertain digit means you have to read between the lines and estimate it. So we need enough grid lines. So that means we need grid lines to the nearest tenth of a milliliter. So we set the grid lines to the tenth of a milliliter, and then we can estimate the uncertain digit, which is standard practice. And so we need grid lines at 0.1 milliliter spacing here. We also need horizontal. These are vertical grid lines. We need horizontal grid lines too. Well, the horizontal grid lines are not so much, we don't really need to pinpoint the pH of the equivalence point. We can. But primarily, what we need to do is this. We need to pinpoint this midpoint here between the start. This would be at 0 milliliters. And this point here at the equivalence point, this is called the equivalence point. And the equivalence point is very important because that's how much base was required to neutralize your acid. But we also need this point here. This point here is you take 1/2 of your equivalence point. So let's say your equivalence point were right on 20 milliliters. Then at 10 milliliters, this is called the 1/2 equivalence point. And all that is you just take 1/2 of the milliliters required to reach the equivalence point. So first we have to determine what our equivalence point is here by graphical analysis, and then estimating it to the nearest 100th of a milliliter.
What if we have, I don't know what it's called, where there's like 2 bumps, like 2 equivalents?
Yeah, this is for monoprotic. We'll talk about diprotic next. So we need 1/2 the equivalence point, and the half equivalence point is special because of this. Let's take a look at the stoichiometry of the half equivalence point. So it doesn't matter what the acid is. This is monoprotic acid, and we're adding sodium hydroxide, the base. And this is going to form, in this case, the NaA plus H2O liquid. Now, we have the initial amount of acid, which we call HA initial. And then we have the initial amount of sodium hydroxide. And we know that the initial amount of sodium hydroxide was not enough to neutralize it. In fact, we could only neutralize how much of the acid. We couldn't neutralize all of it because we didn't add the full equivalent of sodium hydroxide. We only added what we call a half equivalent. And so the initial amount of sodium hydroxide is equal to 1/2 the acid concentration. And so the initial acid concentration here. So we end up with this situation here. The change is we're going to lose half of this acid, so only half of it's going to be neutralized. That means the other half stays unreacted. The sodium hydroxide is a limiting reagent, and so that was there. And then we're going to gain. So the concentration of sodium A, the conjugate base, at the end of this first step here is just equal to 1/2 the HA initial. So the situation comes up here that these two are equal. What type of mixture is this? Can you recognize the mixture? The mixture is HA and NaA. What kind of mixture is that? This is a weak acid, weak base mixture, and it's special because they are conjugates, which means that we call this type of mixture what? The HH buffer. This is equal to an HH buffer. Well, if it's an HH buffer, then we don't have to do step 2. Ice table. Ice table is not required here because we don't have to figure out the equilibrium concentrations. If it's an HH buffer, we skip the ice table and go straight to the Henderson-Hasselbalch equation. And so that's what I'm going to do. I'm going to go straight to the Henderson-Hasselbalch equation. That is, the pH is equal to the pKa plus the log of the base concentration, which would be NaA up here, over the acid concentration, which would be HA in this case. And they're equal. The concentrations are equal. And so it's 1 to 1. In other words, this is going to equal the pKa plus the log of, this is going to be 1/2 the HA concentration initial divided by 1/2 the HA concentration initial. And so that's equal to 1. And so log base 10 of 1 is 0, which results in this. The pH is equal to the pKa. This is very important. This is at what we call the half equivalence point for the titration of a weak acid plus strong base. So when we have this type of titration, we want to know the half equivalence point because we want to be able to determine the pKa for our acid. So we go back up here in our graphical analysis. So what we're going to do in our graphical analysis is, the first thing is we got to determine the equivalence point. Oops, what happened there? We've got to determine our equivalence point. Once we get our equivalence point, then we can get our half equivalence point. Once we get the half equivalence point, then we're going to determine the pH at the half equivalence point here. Because the pH at the half equivalence point is equal to the pKa. And so we need this here. Now we want to get this to the nearest hundredth, so we need grid lines, and the spacing on the grid line should be at 0.1 pH units spacing on the grid lines. That way we can get the pKa to the nearest hundredth. Once we know the pKa of this acid, then that should help us identify it. And so there are two things that we're trying to get here to help us identify. Actually, three things. three, actually, we'll just say three things to get. The first one is it mono or diprotic? There, we could get it from the shape. And so if you had a diprotic acid, we would have two equivalence points rather than one equivalence point. And so if we're looking at diprotic acid, the curve is going to look a little different. Now, it depends on how low you started, how pronounced the first equivalence point is. Normally, the first equivalence point is not very pronounced compared to the second equivalence point. The second equivalence point is larger in general, and that's because it depends on the pH you start with. The higher the pH you start with, the less pronounced this is. Some people start off diluting it with a lot of water. You know, I think the original procedure said add 200 milliliters of water. Well, sometimes what that does is it brings the pH up to here, so when they hit the first equivalence point, they barely see it. And so this has often happened where people will say they had a monoprotic acid when in fact they had a diprotic acid. And the reason they didn't see it is because the first equivalence point wasn't detected. Because the pH that they started. So this is why I asked you to dissolve in the minimum of water. Minimum water will bring the pH down lower, so you might be able to see a more pronounced first equivalence point. But even if you get the pH down low, you know, the lowest pH for weak acid is going to be around pH 2, maybe pH 3, you know, something like that, because it's a weak acid. It's not a strong acid. If it was a strong acid, you can bring the pH down closer to 0. But you're kind of stuck with it. Since the second equivalence point is easier to determine, we start off with that. You know, the more pronounced one, that's going to give us less error. And then we do the same thing. This is graphical eyeball analysis. This is not mathematical analysis that we were talking about earlier. You know. And so we're going to analyze this graphically to find the second equivalence point. And so this would be the second equivalence point here. And then we cut that in half. And that should correspond to this. If we take that volume, cut it in half, then we should get the first equivalence point, which would be half the volume. And so again, we start off with the second equivalence point because that's easier to analyze, and then move on to this by, you know, multiplying this by 1/2. Get that. Now, this is not the half equivalence point. This would be the first because this is the second. And for a diprotic acid, we divide this into quarters. And so what we'll do is we'll take half of this first equivalence point, and that gives us the 1/2 first equivalence point. And so what we'll do is we'll just divide it in half again, the volume, times 1/2. And then what we'll do is we'll come up here and determine what we call pKa1. So the pH at this first one is equal to pKa1. Now what we're going to do is we're going to take this volume here and divide it in half, and then add it to this volume. In other words, we're just going to find the midway point here. And once we find the midway point, then we can determine what we call the second equivalence point. Not second, the 1/2 second equivalence point, I should say. 1/2 second equivalence point. And then cut that over here. And we get the pH is equal to the pKa2 here. So diprotic acids are going to be defined by pKa1 and a pKa2, or Ka1 and Ka2. We can convert the power functions back into scientific notation, non-power functions. It's fine. So this relies heavily on the analysis of this equivalence point, the big one, either the first equivalence point for monoprotic or the second equivalence point for diprotic. And it relies heavily on this eyeball. It's not mathematical. If it were mathematical, well, then we wouldn't rely heavily on eyeball analysis. But eyeball analysis depends on what people do. You know, some people, they want to pick the closest data point. And so some people will have the equivalence point down here below the inflection point because that's the nearest data point. Or some people will have it up here beyond it because that's the next data or the nearest data point. So it's way off here. And so to try to come up with a little bit better analysis of this, you know, the key step is we're going to get some additional confirmation. So we're going to make some additional plots to confirm, or to, you know, this analysis may be wrong, maybe additional plots to better elucidate the equivalence points. And so we're not going to rely just on this plot. So the next plot we're going to make is called a first derivative plot. So I'll do an overlay for the first derivative plot. So this is our pH titration curve. This is going to be for monoprotic here. Monoprotic is going to be flat around here. If you look halfway between the prominent equivalence point here and the initial start, there doesn't appear to be any structure there. This appears to be fairly flat, which is what's expected in the buffer region. pH stays fairly flat. The other plot we're going to generate is something called the first derivative, which looks at the slope. And so the first derivative plot, what that does is it plots the slope versus milliliters. And so we'll take this slope. The slope here is a little, you know, it's rising here, so it's a little bit high. And then it flattens, so the slope kind of goes to 0. And the slope is kind of flat here, and then it starts to rise again. And so the slope is starting to rise again. And then what's going to happen is the slope is going to peak here, you know, at the inflection point. It peaks, and then the slope starts to decrease again. And then it's going to go flat. And so what we're going to see is we're going to see this peak here in the first derivative plot. We can make it bigger. You know, I made it kind of smaller. We're going to make it bigger, but that's basically it. And the equivalence point is going to correspond to the peak, the very peak of this. That's going to be the equivalence point. Now, it depends on how we fit this curve. And so what we're going to do is I'm going to blow this area up here, and then we'll take a look at this in more detail here. Blow this. We have to look at the data here for this peak. It should be fairly symmetric, like this. Now, it depends on how we fit this data. If we use the normal Excel fit, The normal Excel fit draws straight lines between the data points. Do we want to do straight lines between the data point? No. The next Excel fit is, what was it called, the next one? Smooth line or smooth. It's just smooth. But the problem with the smooth is it does something called, it takes the averages of the data. And so the smooth is not perfect. What happens is there's a slight delay in this. And so the smooth curve fit is going to look, actually, it has to go through all the data. So let me try to fix this here. And it's just going to smooth out the jagged edges. So that's the smooth curve fit. Where's the peak of the data? Would you say the peak of the data is here at this data point? That's what it looks like, but it's not really there at that data point. Do you know where it is? It's somewhere in between. It depends on how the smooth curve, sometimes the smooth curve does a good job at this. So sometimes with the smooth curve, what you see is something like this, but it's still a little bit delayed. And so here, you know, the true peak is here. We just didn't see it because we didn't have enough data to map it out, right? We just caught this shoulder of the mountain and this shoulder of the mountain, but we didn't see the peak of the mountain, in other words. And so the best is not to do a standard fit. The best is to do a smooth curve, but a smooth curve is also not the best because a smooth curve, the way the math works, it doesn't. But this peak is defined by a mathematical function. Do you know what the function that defines this peak is called? This one can be defined by a mathematical function. So if it can be defined by a mathematical function, then we can fit it a lot better. And the mathematical function that defines this peak, I'm sorry? No, I mean the name of the mathematical function. What does this peak kind of look like? If it's symmetric, what does it look like to you? What type of peak? Kind of like a parabola, but parabolas would have this kind of thing on the ends. This one's just flat and then up. This is a different mathematical function. This one's called a Gaussian, or normal, or bell. So a lot of people could just call this a bell-shaped curve because it kind of looks like a bell. But most people just call it Gaussian in science because Gaussian is very well-defined mathematical function. Excel, however, you know, Excel was not made for science. Excel was made for what? Yeah. Excel is a finance program, not a science. There are lots of scientific graphing programs. This is one of the standard fits in a scientific graphing program. This is not a standard fit in Excel. Um, wh- what I mean by that is, when we go to insert, let's see if I can do that without having a chart here. Yeah, I'll have to make a chart. So let's say I have a chart like this. This looks like a straight line function to me. So we can right click this and then add a trend line. When I go to the trend line, these are the defaults for the trend lines I have. I have linear, logarithmic, polynomial. I have power, exponential. I don't know why those aren't populating. Moving average. The smooth fit is the moving average fit. And so this is the smooth fit here. This is the r squared value tells us, this is perfectly linear. So if you look at my r squared value, it's equal to 1. It's exactly 1 because the data is linear. I just had Excel made a linear chart here. We could try other trend lines for this. We could try, what other trend lines are there? Oh, I got to go back to my trend line here. We could try logarithmic fit. Take a look at what happens to the r squared value here. .89. Is that a good fit? It's actually, we would consider this a pretty poor fit. We need, although it's pretty close to 0.9, 1.9, it's still not the greatest fit here for this particular thing. We could try other trend lines here with our data. Let's take a look. We could try a polynomial fit. The polynomial fit looks pretty good. We can increase the order of 6th order. This one is, oddly enough, the r squared didn't change much on that. We try moving average. You see the moving average is slightly delayed. The data's off. So this is why the smooth, when I do the smooth curve fit for my plot, the peak is going to be off a little bit. It's going to be slightly delayed. And so when I analyze this and I do the smooth line or smooth curve fit, the peak is off a little bit. Does that make sense? And so what would be the best way to fit this? The best way to fit this is just to graph it in some scientific graphing program and then just ask it to peak pick using Gaussian function, which is normal. Since Excel doesn't do this, it doesn't do this as a default, but Excel will do this as a non-default. And so what you can do, this is a bonus if you're so inclined to do this. If you're not inclined to do this, then it's not necessary to do this. But you can go to YouTube and you can watch a YouTube about how to fit the data using Gaussian in Excel and then just follow the instructions. So, so this would be a bonus. You fit to Gaussian. Once we fit it to a Gaussian, then that should be good. Let's say, once we fit this to a Gaussian, let's try that here. Then we should get a good fit for this. And it doesn't matter where the data point lies. What we're going to look for is we're going to look for the top of this peak. here. Let's say the top of the peak over here. And this would correspond to the equivalence point. For diprotic acid, you're going to see two peaks. You're going to see a big peak here and then a little peak here. And what you want to do is you want to use these, it depends on how your analysis is. You want to either use this as confirmation, if you get a decent plot here, or you want to use this as maybe an equivalent, mode of analysis. That is, you just average the two. And so you take the number you got off the pH plot and the number you got off of the first derivative plot, add those and divide by 2. And then you treat them or weight them equally. The next plot we're going to do is called the second derivative plot. And all that does is it takes the slope of the first derivative plot. So we'll just overlay all our plots here. So let's say this were monoprotic. That's our pH. And then our first derivative plot is going to have a peak here. And then our second derivative plot. Our second derivative plot is going to look at the slope of the first derivative plot. And so the slope kind of stays off on a low here. And then the first derivative plot, which is the blue line, we'll see the slope increase. And then it goes through an inflection point at the halfway up the peak. Halfway up the peak, it undergoes an inflection point and the slope decreases, starts to decrease. And then when I hit the peak here, the slope goes to 0. And then it starts going negative. And then steepens and then comes back. Here. So the equivalence points are going to be like this. Off the pH titration, it's here. Off the first derivative, it's here. Off the second derivative, it's the intercept at the 0. The second derivative might not be as useful if it's quite noisy. So we're going to make these 3 plots in lab. Okay, are there any questions?
So are we going to make the first plot and get the equation and then pick the derivative and that's how we get this?
No, I'll show you. We're going to do it. We'll do it in a different way. Okay, we're going to head over to the computer lab. Let me go unlock it.